I've got an official confirmation that the Zoche AeroDiesel project is alive, and not only alive, but even better than before, now using turbo compounding. And I have all the details to share with you. A few months ago I published this video about the design of the Zoche Aero-Diesel. It wasn't exactly breaking news, but I thought the design was really impressive and I wanted to cover it. A few weeks after posting, I got an email from Georg, lead design engineer at Zoche Aero-Diesels. He congratulated me on the video and then explained that what I covered was actually their engine design from over 20 years ago and that a lot has changed in the background since then. He also brought me up to speed on the current state of the project and shared what they've been up to since going silent and allowed me to share these details with you. Quick note, this video is not sponsored in any way. And while I've done extensive fact-checking with Georg about the design, this is still my interpretation, same as all of my videos. Let's now jump into what happened to the Zoche Aero-Diesel, how the engine design has evolved, and I'll also address some of your questions and concerns from the previous video's comments. I won't cover the basic engine design again, but you can check out the video where I did, linked in the description. When the AeroDiesel was first announced in the mid-1980s, it was truly remarkable. A powerful, lightweight, two-stroke, air-cooled diesel engine with very low fuel consumption. In fact, it achieved efficiency numbers we hadn't seen on aero engines since the Second World War, on engines like the Junkers Humo opposed piston diesel engine and the incredible Napier Nomad, both of which have been covered on the channel already. These two engines were, in fact, Zoche's inspiration for the AeroDiesel. But by the early 2000s, the AeroDiesel wasn't the only aviation-specific two-stroke diesel in development. There were at least two others, the Gemini 3-cylinder opposed piston engine and the Delta Hawk inverted V4 engine, not to mention four-stroke diesels entering the general aviation market. With diesel competition springing up everywhere, Zoche decided to continue development quietly. But that wasn't the only reason for going silent. The AeroDiesel up to that point was a purely mechanical engine with virtually no electronics. The fuel injectors were mechanical and even the engine starter was pneumatic. But something was happening in the late 1990s and gaining momentum by the mid-2000s. The Toyota Prius appeared, the first commercially successful hybrid electric vehicle. Albeit gradually, the world of propulsion was about to change. Earlier I mentioned that the AeroDiesel was inspired by the Humo and Nomad engines. Georg and his father Michael had a dream of creating a turbo-compounded two-stroke diesel, like the Napier Nomad. But the variable speed drive mechanism used on the Nomad that fed recovered power from the turbine to the crankshaft was extremely complex to design. Being quite an unrealistic prospect, they had to put their dream on hold. But when hybrid electric vehicles became a success, they realized that their dream of creating a turbo-compounded aero engine had, in theory, just become possible. Don't worry if you're not sure how hybrid electric cars connect to turbo compounding. We'll get there in a few minutes. To reinforce Zoche's belief that a purely mechanical engine was no longer the answer, Boeing contacted them in 2010, followed in 2011 by EADS, the European Aeronautic Defence and Space Company, who previously owned Airbus. Both were pursuing electrified piston engines that could run on Jet A fuel to replace fuel-hungry gas turbine APUs. An APU, or auxiliary power unit, is a small turbine engine used for several functions on an airliner, mostly when parked on the ground when the main engines are shut down. This includes running the air conditioning, providing cabin lighting, powering electronics, providing compressed air to start the main engines, and more. The problem is that small gas turbines are extremely fuel inefficient. An airliner might sit on the ground for an hour or longer per stop for baggage loading, cabin cleaning and restocking, passenger boarding, and so on. And across multiple flights per day, this adds up to substantial fuel burn that needlessly increases operating costs. Ground power equipment can provide these functions instead, and many airlines use it when available. But APUs remain essential for quick turnarounds and for operational independence, especially where ground equipment isn't always available. With the interest in using a diesel engine as an APU, you may immediately notice a potential problem. Diesel engines are usually very heavy, while gas turbines are extremely light. Isn't it counterproductive to consider the switch? If you watched my previous video on the Zoche Aero-Diesel, you'd know it's extremely light, not only for a diesel, but for a piston engine, period. Boeing and EADS took note of this for good reason. A two-stroke diesel can generate electricity nearly 5 times as efficiently as a gas turbine APU. And the AeroDiesel is actually lighter than some in-use APUs with comparable power output. Many of you may be thinking the same thing, and my first question to Georg was whether they now intend being an APU power plant instead of powering light aircraft. His answer was no. They're still targeting light aircraft, but also APUs, portable generators, marine engines, and several other applications. Doing this is actually very beneficial for a new general aviation engine entering the market in terms of production volume and engine testing. In case you weren't aware, general aviation worldwide is a tiny market compared to most other engine industries. This means any new aero engine is competing against engines that have dominated the market for over 50 years for a very, very small market. Low production volumes push up per unit cost and make it nearly impossible to get established in the aero engine market without massive funding, which almost no one is willing to provide. But by targeting several larger markets, not only does potential production volume comparatively skyrocket, but real-world testing and trust building of the engine happens exponentially faster than is possible with a few dozen engines powering light aircraft. To be clear, the AeroDiesel was designed as an aviation engine, and that won't change. But it can be adapted to a range of different applications. But that still doesn't explain why, decades later, there's still no AeroDiesel on the market, electrified or not. Here, we need to keep several things in mind. With billions of dollars being spent on electrification technology, not only on hybrid cars, but on things like solar panels and wind turbines, it wouldn't have made sense for Zoche to develop electronic components on their own. Additionally, standards still needed to be established. For example, what voltage will be used? They needed to be patient and wait till off-the-shelf components became available. That has since happened, and it became time to design what they call the diesel hybrid power module. The DHPM is an evolution of the Aero-Diesel with few mechanical changes that can deliver power mechanically by turning a propeller with its crankshaft, or electrically by spinning a generator with the generated electricity powering an electric motor that spins the propeller. This has opened up the potential applications of the AeroDiesel tenfold. Think hybrid electric aircraft, which includes VTOLs. This offers an undeniable advantage of allowing a single piston engine to spin multiple propellers mounted anywhere on an aircraft via distributed electric motors. And of course giving at least 5 times better endurance and range than battery electric power alone. The market for this is already here. Now, Electra has already built and flown their hybrid demonstrator, proving the concept for their larger EL9. They use a turbo generator to supply electricity to 8 electric motors. Kawasaki has recently announced plans to start creating hybrid electric petrol power plants for light and medium aircraft, and are also partnering with Volt Aero to power the hybrid Casio 330. And those are just the examples I've covered on the channel in previous videos. An advantage of hybridized piston engines is the ability to increase power to the propeller with a small battery boosting power output. Another benefit of the DHPM producing its main power via a generator is the piston engine can run faster, which increases power output. The propeller-driven version is limited to 2500 RPM, close to the limit of how fast the propeller can spin. Not much faster, and a propeller speed reduction unit would be required. But that's not the limit of the engine. Unaffected by propeller speed limits, the 100% electrified version will have its max RPM increased to 3500. One example where this would be very useful is on seaplanes, which really only need full power to lift the hull out of the water. This means they need oversized engines for that job, but after it's airborne, with the massive drag from the water gone, power required drops significantly. But now they're stuck carrying the oversized engines. The DHPM would be a much lighter engine, with power doubled by the onboard battery on takeoff, then reverting to piston-only power once airborne. But there's something that Zoche DHPM has over virtually every other hybrid electric power plant concept: turbo-compounding. So, how is that enabled? Since it will have the option of generating electricity as its main output, it needs a generator. They combined a starter and generator to handle both electricity generation and engine starting. But it also serves as the first necessary piece to enable turbo compounding. The DHPM will have the option of different sizes of generator. For turning a propeller directly, the minimum spec of the starter generator is 20 kilowatts, which is what is required to start the engine. But the 220 kilowatt or 300 horsepower 8-cylinder variant will also be able to supply all of its power as electricity. Zoche may also offer options between 20 and 220 kilowatts of electric supply if such demand materializes. Okay, now what exactly is turbo compounding? A turbocharged engine utilizes the energy in hot exhaust gases to spin a turbine, which is directly connected to a compressor that feeds compressed intake air into the engine, boosting engine power. The faster the turbine spins, the more air is forced into the combustion chamber. That's good, but the turbine has a limit to how fast it can spin to avoid damage. To prevent exceeding that design limit, it uses a wastegate. When the energy supplied by the exhaust gases would overspeed the turbine, the wastegate opens, releasing some of these gases before it reaches the turbine. But doing so wastes energy. What turbo compounding does is take this excess energy that would otherwise be wasted and use it to help turn the crankshaft. This not only boosts engine power, but since the turbo now helps turn the crankshaft, less fuel is required for combustion, lowering fuel consumption. Historically, turbo compounding has been done with extremely complex variable speed couplings enabling bidirectional power flow, connecting the crankshaft to the turbo, allowing the excess mechanical power of the turbo to be fed to the crankshaft. A reliable, low-cost mechanical coupling is extremely difficult to design. But with the electrification of the Zoche Aero-Diesel, this has become laughably simple to accomplish, at least compared to doing it mechanically. By placing an electric motor generator on the shaft of the turbo, it allows the turbo to compound the engine, not mechanically, but electrically. The motor generator on the turbo shaft acts as a brake on the turbo to prevent overspeed, and like an electric car's regenerative braking, this generates electricity. On the DHPM, this electricity is routed to the starter generator connected to the crankshaft. Whenever there's excess energy in the exhaust gases, the e-turbo will capture and send that energy to the starter generator, which helps turn the engine. At full power on the 220 kilowatts engine, there's roughly 100 kilowatts of power at the turbo, of which 20 kilowatts is available to use for free, which is fed to the crankshaft. This results in a 9% increase in power and efficiency. But I've neglected to mention something important. One of the biggest changes from the old AeroDiesel to the DHPM is the supercharger, which has been removed. As with any two-stroke diesel, a supercharger is required for scavenging, as it's generally not possible to scavenge with an exhaust-driven turbo alone. It takes higher RPM before the turbo creates enough boost, so it wouldn't be able to scavenge at low crankshaft RPM. But remember, this turbo has an electric motor on its shaft. We can use electricity to spin the turbo at low RPM, so it can now be used for scavenging. How neat is that? Remember that 9% power increase I mentioned? That's actually incorrect because the supercharger the old AeroDiesel used to have was turned by the crankshaft. That makes it ideal for scavenging a two-stroke diesel, but it also robs some power from the crankshaft. It takes power to spin a supercharger. In the case of the AeroDiesel, about 20 kilowatts at max power. By no longer requiring a supercharger, we gain back those friction losses. Being conservative and keeping added electrical losses in mind, Georg expects their turbo compounding solution to add 30 kilowatts of additional power and a 12% efficiency increase over the old 8-cylinder Aero-Diesel. That's a specific fuel consumption improvement from 225 grams per kilowatt hour for the old Aero-Diesel to 198 on the DHPM. If that's realized, this will be the most fuel-efficient piston internal combustion aviation engine ever produced, according to my findings at least. And yes, that beats the legendary efficiency of the Napier Nomad 2. Efficiency is not the only area where the DHPM will be king. The other is power to weight ratio, and there is no other diesel aero engine that comes close. But does that mean the engine is extremely stressed to achieve this at such a low weight? Actually, no. BMAP is quite low, and mean piston speed is a moderate 11 meters per second. By the way, that's at the increased 3500 RPM. This indicates it's not a highly thermally or mechanically stressed engine, and it should have no problem achieving the 2000 hours TBO. Adding to all of this is that it doesn't require high complexity to achieve. No valves or valve train, no spark plugs or ignition system, no supercharger, no wastegate on the turbo, no gearbox, no heavy master and articulated conrod setup, and no complex mechanical power transfer system. Compared to the old engine, this one has more power, better efficiency, and lower complexity. I wanted to cover some concerns raised in the comments of the previous video. Quite a few said air cooling a diesel would be problematic, and that is, some said, a likely reason for the AeroDiesel's failure to come to market. We now know that's not the case, but let's address the technicalities of air cooling a diesel. I mentioned in the previous video that diesels don't have any localized hotspots forming during combustion, since combustion isn't started with a spark, but via fuel sprayed into very hot compressed air. The fuel spray is spread out, resulting in more distributed combustion, and combustion happens slower than the rapid flame front present in spark-ignited petrol combustion chambers. In addition to that, keep in mind we're talking about a two-stroke diesel. That is an important distinction from a four-stroke engine because of how scavenging happens. On the two-stroke diesel, various design tricks are employed to make sure that when the piston exposes the intake port, not too much of the fresh, cool intake air is lost via the open exhaust port, like using loop scavenging, for example. But ultimately, some of that intake air is lost, unburned out the exhaust. This is usually argued as being less efficient, but this also has an advantage, which is cooling. This scavenge loss is cool intake air moving over the piston, through the cylinder and out via the exhaust port. This cools down the engine from inside. also keep in mind that these losses aren't that expensive in terms of efficiency because it's not an air and fuel mixture lost out the exhaust, but simply clean intake air. And don't forget, some of that scavenging air efficiency loss is recovered by the turbo. To illustrate the cooling properties of the engine, Georg shared with me something interesting. Here's a single cylinder of the AeroDiesel next to one of a Wright R3350, the 18-cylinder air-cooled radial used in late and post-World War II planes like the B-29 bomber and the A-1 Skyraider. The ratio of cooling fin to internal surface area exposed to hot combustion of the AeroDiesel is roughly double that of the R3350. I thought that was quite a fun fact. Also, I think this puts the cooling concerns to rest. Something else I can't neglect to mention, or someone will comment it's because of cooling issues, is the DHPM will not only be available as an air-cooled engine, but also as a liquid-cooled engine. And no, this is not because of air cooling problems. Georg was adamant that for aviation applications, air cooling is the way to go. The liquid-cooled variant will be exclusively for non-aviation applications where air cooling would be insufficient, like generators, emergency water pumps, and marine applications. The other concern raised in the previous video's comments is regarding the slipper-type bearings and connecting rods, which don't fully enclose the crank pin, only the top, with just lightweight webs to keep it in place. Same for the connection at the wrist pin. Check out the previous video covering the genius advantages of doing this. But this was cited as another reason for the engine's failure to come to market. Again, this is not the case. In a 4-stroke engine, the piston can be moved in 3 ways. First, being pushed down by combustion during the power stroke. Second, being pushed up by the crankshaft via the crank pin during the compression and exhaust strokes. But there's a third way, the piston being pulled down by the crankshaft during the intake stroke. This is a different type of loading on the bearing and conrod than the other two, a tensile load or a pull, and the conrod needs a full enclosure to be able to handle that pull. But this tensile load doesn't exist in 2-stroke engines. During the downward stroke, the piston is pushed down by combustion, and during the upward stroke, it's pushed up by the crank pin. There are no pull loads. A popular counter-argument to this is, what if an injector fails on one of the cylinders, resulting in no combustion happening? No push from combustion means there would be a pull load via the crankshaft, and the crankpin, conrod and piston would separate. But this is not the case. Even in the event of an injector failure, compression still happens on the upward stroke. With a compression ratio of 17:1, at top dead center, pressure in the cylinder is around 660 psi, which then pushes the piston down with a force equivalent to about 3 tons. Georg has even demonstrated this before on testbed engines, pulling the injector plug of 1 cylinder, 2 or even 3 cylinders. Other than for a power loss, nothing happens. The engine keeps running with no destruction happening. A comment I got a few times was regarding emissions and that a 2-stroke will never meet emission standards. Emissions get complex here and I don't have time to cover it comprehensively in this video. But here's the crux of it. We need to reinforce a few points. First, this is not a gasoline 2-stroke with a total loss lubrication system where the scavenged air loss is a mixture of unburnt air, fuel and oil that's lost via the exhaust. On the pressure lubricated dry sump system of the Aero-Diesel, fuel is injected directly into the cylinder during operation and oil is pressure fed to internals. So that scavenging loss is only clean air. The e-turbo, other than making a supercharger redundant, can actually reduce emissions compared to using a standard turbo if utilized correctly. Since the e-turbo can be operated electronically, we have precise control over it. It can thus be used like an EGR or exhaust gas recirculation unit. By controlling boost pressure, the amount of residual gas remaining in the cylinders can be finely controlled, which reduces nitrogen oxide emissions. In conjunction, good exhaust gas after treatment will be used. As Georg mentioned, they want to build the cleanest possible engine, even if not forced to do so by regulation. And yes, this can absolutely be used on a two-stroke diesel. The long and short of it is, emissions of the DHPM will be at least on par with comparable four-stroke engines. Earlier I stated that the injectors on the old Aero-Diesel used to be mechanical injectors. With the DHPM being electrified, it doesn't make much sense keeping the injectors mechanical, does it? Zoche has developed their own common rail injection nozzles, specifically designing it small enough not to enlarge the engine's cross-section, and this is what you're seeing on screen. I can already hear the complaints that it won't be as reliable as the old-school mechanical injectors. But Zoche test bench engines have actually been running with common rail injection since before the year 2000, it just wasn't made public before. So that concern can also be put to rest. Since the DHPM will be electrified, it needs a battery to store some energy. Some would see this as just additional weight and complexity. Weight, yes, but complexity, not really. But even with weight, it depends on the application. On the minimally electrified version used to mechanically spin a propeller on a light aircraft, the weight of the removed supercharger essentially offsets the added electric components, resulting in virtually no net weight increase. For the fully electrified version that only generates electricity, it depends on the application and how much energy the designers of that aircraft want to store. For this, the weight increase due to the generator and inverter is only 36 kilograms. Georg did mention that this will be further reduced with the development of modern electronic components. I know what many of you want to know now is, when can I have one?
Shut up and take my money!
Georg indicated that it will take about 3 years to build the prototype, depending on a few things like funding and partnerships. Up to now, this has mostly been a self-funded project. What about how much one would cost? It's too early to give an accurate estimate in my opinion, which I know is not what you want to hear, but it is what it is. Georg did mention that thanks to being aimed at much larger markets than aviation, the higher production volumes combined with the very low parts count gives it the potential to be produced at much lower cost than would typically be possible. I'd like to thank Georg for all the information and for allowing me to share this news. If I've missed anything important, feel free to reach out to Georg himself to hear it straight from the horse's mouth. His email address is in the description below. Also, thank you for watching. Let me know your thoughts on the DHPM in the comments and see you in the next one.